All right, so sampling distributions for the mean when the underlying variable is normally distributed or the sample is greater than 30. They look like this. Where we have the mean on the x-axis and the probability on the y-axis. The distribution itself is bell-shaped, with the overall mean at the center, which is the greatest probability, and the standard deviation tells you how narrow or how wide the distribution is. And we can say that all sampling distributions for means when n is greater than 30 are going to have this shape. And as I said before, the mean and standard deviation for this distribution are going to be based on the characteristics of the underlying probability distribution. In other words, the probability distribution for the variable you're interested in. So if your variable is x and you're looking at x bar, which is the mean, you're going to be looking at the probability distribution for x. But you don't actually have to do much in order to fill in these values. So a nice thing about central limit theorem is that a couple of things are always going to be the case. One is that the mean of your your sampling distribution is always going to be equal to the mean for the variable that you're looking at. So whatever your variable is, the population mean for that variable is going to be equal to the mean for your sampling distribution. And what this means is that the most likely mean value that you're going to get is the overall mean for the population. And this should match what we were talking about with sampling. So the most likely thing to happen is that your sample mean is going to be the same as your population mean. But it can differ. And what this sampling distribution tells us is that the way it differs is that it's most likely that you're going to get a sample mean that's close to your population mean, so you're not too far off in either direction. And then the farther away you go, the less likely the sample means become. So it's really unlikely that you're going to get a sample mean that's really much bigger than your population mean. And it's also unlikely that you're going to get a sample mean that's much smaller than your population mean. The standard deviation for your sampling distribution is going to be based on what we call the standard error formula. And again, the standard deviation for the sampling distribution is called the standard error overall. And the formula for calculating standard error looks like this. You have the standard deviation for your variable, and you're going to divide it by the square root of the sample size. And that's your standard error formula. So the standard error for your sampling distribution, which again tells you how narrow or how wide your bell curve is going to be based on two things. One is how narrow or wide the distribution for that underlying variable is. That's your standard deviation for the variable. The other thing is the sample size. And since you're dividing by the sample size, the bigger your sample size is, the smaller your standard error is going to end up being. And now I'm going to go through all of this with an example. And specifically, we're going to be looking at that same example that we were using to talk about the normal distribution last week, which is a probability distribution for thefts in stores. So what I'm going to write out here is the probability distribution for thefts occurring in a particular store. And so this should look pretty familiar because this is going to be the same thing that we were looking at all week last week, where the variable itself is number of thefts. We're looking at probability. And we had a mean of 65 thefts, making that the most likely number of thefts we would expect, and a standard deviation of 15 thefts, which tells us about how spread out these different possible values are away from our mean. What we're going to say is that this is a sampling distribution for the number of thefts at a chain of stores. So there's actually hundreds and hundreds of stores across the country. We'll call them stat smarts. And so this sampling distribution describes the probability of the number of thefts you'd see in a week at any particular stat smart. For this example, though, we're going to be taking a sample of 30 stat smarts. So 30 is the cutoff where we know that the central limit theorem applies. And in this case, we actually have a normal distribution for our underlying variable, so we would get a normal distribution for our sampling distribution even if we had a smaller sample than 30. But we're going to say we're going to sample 30 stat smarts. So we're going to take the 30 of these stores and we're going to look at the number of thefts that occurred in each store. And what we're going to do is we're going to calculate the mean number of thefts in those 30 stores. So the statistic we're interested in is going to be the mean number of thefts in 30 of these stores. And what we're going to do here is draw a sampling distribution that describes this value here, which again we can also call x bar. So it's going to be sample mean. And what the sampling distribution is going to tell us is the likelihood of getting different mean values in our sample of 30 stores. And our mean is going to be, again, mu x bar, and our standard error, which again is the standard deviation for a sampling distribution, is going to be written as sigma sub x bar. And here, what we're looking at the bottom is the mean number of thefts in our sample of 30. And so the sampling distribution tells us a few things, even without the numbers filled in. It tells us that there's going to be some mean number of thefts, that's the most likely, and as you get away from that, it becomes less likely that that's going to be the mean number that you actually see in your sample of 30 stores. What we're going to do now is fill in these different values in our probability distribution. The first one, which is the mean for the sampling distribution, is just going to be equal to the mean for our variable. So we're going to say that the mean for the sampling distribution is going to be equal to the mean for the variable. The mean for the variable, as we know, is equal to 65. Which we can see here. And I just also wrote out right here. So the mean for your sampling distribution is going to be equal to the mean for your probability distribution. This means that our mean is going to be equal to 65. So we know that the most likely mean value that we're going to get is a mean of 65. So we've taken these 30 stat smarts, we're wondering what the mean number is going to be in our sample of 30, and we know that the most likely value that we could get is going to be 65 thefts. And again, this goes back to the idea that your sample typically resembles your population. And here the population value that's most likely is 65, so the sample value that's most likely is going to be 65 as well. We can also find the standard error for this distribution. And the standard error, as I said, is given by this equation, which is the standard deviation for the variable divided by the square root of the sample size. So these are just numbers that we can plug in. We know that the standard deviation for our variable is 15 thefts. So we can plug that in for standard deviation. The sample size are the number of cases that are included in the sample itself. So here we have a sample of 30 stat smarts. Our sample size is 30. And I'll just write this here. So this means that n is equal to 30. Anytime you see, a sample of or sample some number, that's your n. So now we can just do the math to find our standard error for this distribution. And if you divide 15 by the square root of 30, you should get a standard error of 2.74 thefts. So this tells us that the standard error for this distribution is 2.74. So now we have something that looks a whole lot like a regular normal distribution, where we have our most likely value. So it's most likely you're going to get a mean of 65. And then we have a number that tells you how spread out this sampling distribution is, and tells you how closely these possible sample means are bunched around your most likely mean of 65. So it's very likely you're going to get a sample mean over here. It's unlikely that you're going to get a sample mean that's much higher than 65. Unlikely that you're going to get a sample mean that's much lower than 65. I also want to demonstrate a couple other things here. So now that we have a normal distribution, we can treat it like any other normal distribution. We can do a couple of things. One thing that we can use is that 68, 95, 99.7 rule. So I'm going to redraw this here and tell you some things about the samples you're likely to get just based on this sampling distribution. So we have number of thefts, which is x bar. We have a standard deviation of 2.74. Our mean is equal to 65. If you recall from last week, the 68, 95, 99.7 rule tells you what proportion of area under the curve falls within 1, 2, and 3 standard deviations of the mean. It tells you the same thing in a sampling distribution. So here we're going to look at one standard deviation on either side of the mean. So to get to this line here, we're going to be looking at one standard deviation to the positive side of the mean. And in order to get there, we have our mu plus one standard deviation. In other words, we're looking at 65, which is the mean, plus 2.74. 65 plus 2.74 comes out to 67.74. So that's one standard deviation jump away from the mean in a positive direction. We can also go in the other direction, so 2.74 in this direction, and we'll get mu of x bar minus one standard error. In other words, 65 minus 2.74. And if you subtract 2.74, you get 62.26 right here. So thanks to the empirical rule, we can take a look at this and we can say that within one standard deviation of the mean on either side, we know that we're going to have 68.3% of our area. This means that we have a 68.3% chance of getting a value that's within these two values, so between 62.26 and 67.74. In other words, we could say that there is a 68.3% chance of getting a sample mean between 62.26 and 67.74. So in other words, we're using the empirical rule in the exact same way that we did before. The only thing that's different is that we're now counting out in terms of standard errors instead of in terms of standard deviations. But it gives you the exact same information and it works in exactly the same way. So if you count out one standard error on either side, you know that there's going to be a 68.3% chance of getting a sample mean in between those two values. So again, same concept. The only thing that's changed here is that now we're looking at sorry, this is a little crunched, but now we're looking at mean values instead of individual values. So in our 30 stores that we sampled, there's a 68.3% chance that the mean for those 30 stores is going to be between 62.26 and 67.74. And so you could do the same thing going out 2 or 3 standard deviations as well. And I'm not going to go through the example now, but I'm going to write out here, same thing for plus or minus 2 standard errors and plus or minus 3 standard errors. So for 2 standard errors going out on either side, you would again use the rule, which would give you 95.5%. And going out 3 standard errors on either side, you could use the rule, which would give you 99.7%. So same exact idea as last week. The only thing that's different is that we're now using the values that we filled in for our sampling distribution. And what we're finding the probability of is the mean of those 30 stores that we took a sample of. So you can also find Z-scores. And you can use them in exactly the same way as you would a z-score in a regular normal distribution. But what a z-score tells you here is how many standard errors away from the mean are you? Is a particular sample mean. Particular sample mean. So if you remember before, a z-score told you how far away from the mean a particular value was. In this case, we're just changing out the terminology a little bit because we're looking at a sampling distribution. So we're looking at how many standard errors, same thing as standard deviations, we are from the mean for a particular sample mean. And so this mean that I'm referring to here is going to be your overall mu of x bar, and for a sample mean, we're going to be talking about x bar, the mean for your particular sample that you take. And so I'll put up an example here as well, where our sampling distribution has a mean of 65, has a standard deviation of 2.74, and now we're interested in how many standard errors away from the mean we would be if we got a sample mean of 60. So I'll write it like this. So we're looking at mean number of thefts, looking at probabilities, and we want to know how many standard errors away from this mean a sample mean of 60 would be. And to do this, we're going to use the z-score formula for a sampling distribution. The nice thing about this is that it's exactly the same as the z-score formula for a probability distribution. We're just writing out our mu of x bar and our sigma of x bar instead of regular mu and sigma. So the z-score for a sampling distribution is going to be given by x bar minus mu of x bar divided by the sigma of x bar here. So it's exactly the same as the z-score that you looked at last week. The only difference is that now we're looking at a sample mean instead of a particular value or outcome, and we're looking at our overall mean of sample means here, mu of x bar, and the standard error for our sampling distribution. And I'll just write this out here. That's where x bar is equal to the sample mean. Mu of x bar is the overall mean, and sigma of x bar is the standard error. So in order to find the z-score for 60 thefts here, we're just going to plug stuff into the formula. So for 60 thefts, we're going to do what we did last week. The sample mean that we're interested in here is 60. So we're interested in how far away a sample mean of 60 is from our overall mean here of 65. So we're going to plug in 60 for x bar. Next, we're going to subtract our overall mean here in the sampling distribution, which is 65. And finally, we're going to divide by our standard error. And our standard error is what we calculated, which is 2.74. So one thing, if you're doing one of these problems, just remember to use the standard error, which you may have to calculate yourself first, and not the standard deviation for the variable. You want to use the standard error for the sampling distribution. So now that we have this stuff plugged in, we can do the math, and 60 minus 65 over 2.74 comes out to negative 1.82. This tells us that we are negative 1.82 standard errors away from the mean, going towards the left. So if you're counting in standard errors, or jumps of 2.74, you're 1.82 jumps away from the mean here. This also means that if you were to convert everything into z-scores, you could describe this using a standard normal distribution. So right here, I'm just drawing our standard normal distribution, which has units that are z-scores. So we've converted our mean number of thefts here just to straight up regular z-scores. We have a mean of 0, a standard deviation of 1, and we can plot our sample mean of 60 on the standard normal distribution as well. So we can say x bar is equal to 60 is going to be at negative 1.82 z-scores on here. And so with this, you can also use the z-table, so we have a shaded area between this and the mean. And we can otherwise treat this exactly the same as a different standard normal distribution and do anything else you would do with it. Again, the only difference here is that what we're talking about is a possible sample mean that you could get rather than a possible value. And with that, I'm going to close out this lecture. So just remember that it's pretty much just a normal distribution, and have a good week.